Hafade, my name is Guillaume Paras. I am an undergraduate student at the University of Guam. Today, I will be talking about our research project titled A Compartment Model for Schistosoma japonicum Transmission Dynamics in the Philippines. This research project was part of a collaborative effort under the University of Guam REU and the YSREM programs, where I'd like to acknowledge our co-authors, Wanjen Ko, Tayo Tagami, and Claire Yi. Here are the contents of my presentation. Our research will be focusing on schistosomiasis. Schistosomiasis is a chronic and debilitating neglected tropical disease, or NTD, which is second only to malaria as one of the most devastating parasitic diseases. In 2021, it was estimated that 251.4 million individuals require treatment for schistosomiasis. The disease is caused by a parasitic flatworm of the genus Schistosoma, and infection occurs when skin comes in contact with contaminated freshwater that contains schistosome-hosting snails. The disease is especially prevalent in areas where access to clean water, sanitation, and healthcare is especially difficult. If you take a look at figure 1, this is the life cycle of schistosoma. The cycle begins when eggs are shed from an infected human, either through their feces or urine. From there, the eggs hatch and release myristidia, and the myristidia penetrate the snail tissue. In the snail, sporocysts develop, and free-swimming cercariae are released into the water, which then penetrate the human skin, and the cycle repeats itself. Specifically, we wanted to focus on schistosomiasis in the Philippines because it's an ongoing public health challenge in many endemic regions of the country. In 2018 alone, around 800,000 individuals were diagnosed with infection, and 12 million people remain at risk of contracting the disease. Schistosomiasis is prevalent in the 3 major island groups of the Philippines, where these regions are characterized by non-dry seasons and are predominantly rice-growing areas that facilitate interactions between humans and freshwater snails. Schistosoma japonicum remains the predominant species responsible for human infections, and the transmission dynamics are known to involve additional mammalian hosts. In the Philippines, the substantial presence of water buffaloes, commonly referred to as carabaos, play a significant role in the widespread transmission of the disease in the country. Our research goal is to develop a comprehensive mathematical model that effectively captures the dynamics of schistosomiasis in the context of the Philippines. Our model will consider the interactions between humans, snails, and bovine populations to accurately simulate the transmission of the disease. We will be focusing on the effects of freshwater contact reduction on schistosomiasis transmission, and we will demonstrate that when contacts are substantially reduced, for example, by increasing the mechanization level, the disease can be eliminated. Moving on to our compartment model, we considered 3 host populations: humans, bovines, and snails, which are denoted as capital H, B, and G. Humans and bovines will act as definitive hosts, and snails will act as intermediate hosts. We also consider the following free-ranging stages of schistosoma: the eggs, myristidia, and cercariae, which are denoted as capital E, M, and C. We divided the human population into the following compartments. We have the susceptible, which is denoted as S sub H. We have the latent infection, which is denoted as L sub H. We have the infectious, which is denoted as I sub H. And we have the recovered, which is denoted as R sub H. The snail and bovine populations will be divided into only the susceptible, latent infection, and infectious compartments. And this is due to the assumption that snails cannot be reinfected and cannot recover, and bovines are not treated for the disease. Here is our compartmental model. Due to time constraints, I won't be able to go through this in detail. However, it's important to note that the yellow compartments represent the human population, the green compartments represent the snails, the brown represent the bovines, the blue compartments on the right represent the myristidia and the eggs, and the pink compartments represent the cercariae. If you take a look at a closer look at one of the compartments, this is the S sub H compartment, which represents the susceptible humans. The arrows pointing into the compartments represent the rates coming in, and the arrows pointing away from the compartments represent the rates coming out. We have lambda H, which is the birth rate, mu H, which is the death rate, and beta HC, which represents the individuals who become latently infected at the time after coming into contact with the cercariae. Our previously described model yields these following system of differential equations. And to model the effect of freshwater contact avoidance, we will assume that beta H is equal to 1 minus RH, beta H 0. R sub H represents the proportions at which human populations implement the control method, and beta H 0 is the transmission rate at the baseline. The bovine populations follow a similar progression where beta B is equal to 1 minus RB, beta B 0. Here are the parameters that we will be using for our model. Specifically, I'd like to point out R sub H and R sub B, which represent the control method of avoiding freshwater contact for both humans and bovines. For analysis, first, we solve for the disease-free equilibrium. This is a 13-tuple of constant solutions to the system of our differential equations, for which there is no parasite present in the population. After solving for disease-free equilibrium, we end up with S sub H, S sub G, and S sub B equal to the birth rate over the death rates. We will determine the local stability of our disease-free equilibrium using the basic reproduction number, or R0, which we found using the next generation matrix method. And by plugging in our parameter values, we obtain an R0 value of approximately 4.42 at the baseline. This means that in a completely susceptible population, a typical fertile adult worm would on average produce 4.42 female worms during its life. We do want R0 to be less than 1, which then on average, one egg generates fewer than one new egg in the next generation, preventing schistosomiasis from spreading. At this time, the disease-free equilibrium is locally asymptotically stable. Here is our endemic equilibrium, which is an equilibrium where the parasite is still present in the population. And moving on to the results, we conducted a sensitivity analysis to determine how different values of an independent variable affect a particular dependent variable under a given set of assumptions. We conducted our sensitivity analysis of our basic reproduction number based on areola and hymen, and the sensitivity index of our R0 on a parameter P is defined as P over R0 times partial R0 over partial P. Here are the results of our sensitivity analysis. Just looking at figure 4, you can see that the snail-related parameters have the higher sensitivity values, followed by the bovine-related parameters. We also have the human-related parameters, which have a lower sensitivity value. Here is a visual representation of our sensitivity analysis. Here we show only the parameters for which the absolute value of the sensitivity index is larger than 0.05. These graphs show us the dependence of our basic reproduction number on both R sub B and R sub H, which represent the control method, which is the avoidance of freshwater contact. If you take a look at the first graph, you can see that reducing bovine freshwater contact can reduce our basic reproduction number. However, if you take a look at the graph on the right, for humans, we can see that implementing the control method does not have any effect on our basic reproduction number. Once again, based off of our sensitivity analysis, we saw that the effect of the snail-related parameters is the most profound. The effect of the human-related parameters, on the other hand, for the reproduction number is negligible, and the control strategy of freshwater avoidance by humans has almost no effect on our basic reproduction number, which is in sharp contrast with the same control strategy for carabaos. In our research, we are primarily interested in seeing whether it's possible to eliminate schistosomiasis by avoiding contact with fresh water. Since the effects of R sub H on the basic reproduction number are negligible, we set for simplicity R sub H equals to R sub B. This is what we end up with, and we see that at least 77% of the bovine population must avoid contaminated freshwater sources in order to break the schistosomiasis cycle and eliminate the disease. These graphs show us the prevalence of human and bovine infections over time. And based off of these two graphs, we infer that if the contact between bovines and freshwater is reduced by about 80%, the prevalence of human infection would decrease by over 50%, approximately every 10 years. The current prevalence of 2% could be reduced to under 1% in 10 years and to under 0.5% in 20 years from now. Reducing the contact between bovines and water by 90% would speed up the elimination even more, and the prevalence of 0.5% could be reached in about 10 years. We can also see that reducing the contact by 50% will reduce the disease prevalence by about 25%. And while this effect could be felt within 10 years, no further significant decrease of prevalence would follow afterwards. For our discussion and conclusion, we created and analyzed a compartmental model depicting schistosomiasis disease dynamics in the Philippines. We expanded on existing schistosomiasis models to consider the different life stages of Schistosoma japonicum, the human, snail, and bovine populations. We considered the latent periods of Schistosoma japonicum in the 3 host population, and we considered the recovery and acquired immunity in humans. Our compartmental model is more robust than previous models of schistosomiasis disease in the Philippines due to the greater inclusion of detail. Chen et al. Use a conceptually similar model, although they involve only susceptible and infectious compartments for each population and did not explicitly consider Myristidia and Cercariae. The model in Ishikawa et al. Is similar, but considers rats instead of bovines and does not consider a recovered compartment. We derived the formula for the basic reproduction number, and based on model calibrations, we estimated the R0 value to be approximately 4.42. Our strategy for effectively combating schistosomiasis disease transmission focuses on reducing infection rates by reducing the contacts with freshwater sources. We have shown that the reduction of bovine contact with water by about 77% can eliminate schistosomiasis, and we argue that it could be achieved by increasing the mechanization level, which is already planned in the Philippines. Our numerical simulations demonstrate that the effects of contact reduction could be felt within 10 years. Water contact reduction does not have to be the full 77% required for complete elimination. When water contact reduction is about 50%, disease prevalence in humans will drop from the current 2% to about 1.5% in 10 years, but will not change much afterwards. Water contact reduction by 70% would achieve the disease prevalence under 1% in slightly more than 10 years. And the potential elimination of schistosomiasis should be considered as an additional benefit of the mechanization efforts in the Philippines. To improve our research, here are some things we can consider in the future. With schistosomiasis, other hosts are involved in transmission, and incorporating these hosts would make the model more precise. However, at the same time, Raj et al. Showed that the bovine is the most critical to transmission, so incorporating other hosts does not substantially alter the qualitative results. We can also consider how seasonality affects the dynamics of schistosomiasis in the Philippines. In our model, we assume that seasonal and weather variations do not affect the snail, Myristidia, and Cercariae populations. Here are our references that we use for our research. And once again, due to time constraints, I was not able to go in much detail about our research project, but if you guys are interested, our research project has been published, so you can take a look at that. I would like to thank the UOG-REU and the YSREM for allowing us to do this research project. And most of all, I'd like to thank my mentors, Dr. Hyunju Oh, Dr. Richter, Dr. Taylor, and Dr. Aquino for assisting us throughout this research experience and assisting us with getting our research paper published. Thank you so much.